department in the areas of geometry and mathematical physics. And today we have my collaborator, a friend from a long time, Professor Lawton from Johns Hopkins University. He will be talking about flawed groups. Thank you.
All right, well, thank you very much, Carlos. And of course, I thank the organizers as well for having me and of course, the invitation. It's always a pleasure to be in Lisboa. I'm a bit of a Lusophile, and I love Portugal very much. Okay, without further ado, let's go ahead and get started. So I'm going to be talking about collaborative work with Carlos Florentino. In particular, we have a new paper out that concerns a type of group that we've called flawed groups. And it's essentially a paper that kind of crystallizes many years of research and puts together a number of ideas from quite a while ago, and also pushes the boundary of what's known about this class of groups. Okay, so here's an outline. Let's see, is the little red dot visible on the screen? Yeah, on the YouTube? Yes? Okay, because I do have an alternative. You see, if the little red dot doesn't work, I can use the bamboo. So we have multiple options here. But anyway, okay, so we'll go with the high-tech version. So first I'll tell you a little bit about character varieties. This is a type of moduli space that is the sort of lens that we're going to look at groups through to define this class of groups. I'll quickly go through some examples that if you've seen me give talks, this is my usual list of very simple examples just based on linear algebra ideas to just illustrate some of the what's involved in defining these moduli spaces. Then we'll get to the definition of flawed groups, talk about past results, new results, and conjectures and questions. Okay, so all right, so the first ingredient to define a character variety I think of as a topological ingredient, and it's a finally presentable group. I usually think of it as a topological ingredient because often enough it arises as a fundamental group of a compact manifold or orbifold. But it doesn't have to arise in that way. You can just think of it as a collection of symbols, your generators, subject to some conditions, the relations. And since it's finitely presentable, there's a finite list of generators and a finite list of relations. The relations are words in this letter, in this set of letters, characters. Okay, so some examples are free groups, free abelian groups, and like I said, more generally, you can think of every finitely presentable group does in fact arise as some compact, fundamental group of some compact CW complex, topological space. And in these examples, you can think of them as compact manifolds. So in this case, it's like a surface with a boundary. Here, you can think of this as a product of circles. M is. Okay, so a very simple example is just one generator and a one relation of the form like gamma to the n, and then you just get the cyclic group of order n. Okay, all right. All right, so the second ingredient for a character variety is a Lie group, and the class of Lie groups I'm going to concern myself with the story of them begins with a compact Lie group. As a general fact, every compact Lie group is the zero set of a bunch of real polynomials, a real algebraic group. And consequently, you can look at their complex zeros, okay, the zeros over the complex numbers. Okay? And every group that arises in this way is what's called an affine algebraic reductive group over the complex numbers. And there's other ways to define reductive affine algebraic groups in terms of something called the radical or the unipotent radical. And over the complex numbers, it's equivalent to this definition, so we'll just leave it at that. And then if you look at with respect to some model for this algebraic group, so some choice of polynomials, okay? You can say, well, you can go backwards and say, what are the real zeros? Now, it doesn't necessarily get you back to K. Okay, there are different polynomial models and different over R, and different real loci will give you different groups here. A good example of that is if you look at the, say, the simple linear SUN, right, and then you look at the complex zeros of a natural set of polynomials that cut SUN out of, say, you know, just n by n matrices. Okay, you get something isomorphic to GLNC, or sorry, SLNC, right? But this, of course, has, you know, is the zero set of a collection of polynomials that started off defining the unitary group here, right? But there's also another model, namely just the determinant minus 1, right? And if you look at the real locus with respect to that model, you just get, right, SL and R, right? Which is not back where you started. But both of these complexify to the same thing, right? Okay. All right, all right. So if you look at any subgroup of the real locus with respect to some model, and you demand that the identity component is there, and it's Zariski dense, then we'll say that's real reductive. Okay, and that's a sort of definition. The examples, you know, are the usual ones: SLNC, SLNR, unitary groups, the orthogonal groups, etc. All of these are examples of real reductive groups. Okay. So relating the finally generated group to a Lie group, right? We can just naturally consider the set of group homomorphisms from gamma to G. Okay, and we want to put a topology on this set, and since gamma was assumed to be generated by little r elements, right, back to the right here, right, little r is there, right? We can then, and a homomorphism is just determined by where you send the generators of gamma, right, because it has to satisfy the homomorphism condition, right? There's a natural map called the evaluation map, which just sends a homomorphism to the tuple of evaluates of its generating set. This map is always injective, not generally surjective. If gamma was a free group, it is bijective. But usually you have to ask the question, you know, when does a given tuple satisfy the relations of gamma, right? And that exactly defines the image. But the bottom line is this identifies this set as a subset of a natural analytic manifold, right? G to the R, because G was a Lie group. And so, and in fact, you know, if G was algebraic, the conditions defining the image will be given in terms of polynomial data as well. It's just the words, right, defining the relations in gamma, right? Of course, in the entries of G, but if G was algebraic, that does result in a set of polynomial conditions. And so this defines a subvariety, either analytic or semi-algebraic or algebraic, depending on what G was, the structure on G. But the bottom line is it gives you a natural topology. And that topology is independent of the presentation of gamma in the sense that if you gave me a different presentation, I'd be able to come up with a natural map between the two different resulting topologies on Hom, one corresponding to the, you know, basically corresponding to the isomorphism on the level of the two different presentations of the group, right? And that would give you a homeomorphism on the on Hom, the two different topologies on Hom. So it's independent of the presentation of gamma up to this homeomorphism. Okay, so what's next, right? We want a natural equivalence relation on this collection of homomorphisms, and if G was, say, GLN, right, then you are talking about representations of gamma, okay? And in general, this class of groups G, Lie groups G, always has a faithful representation in some GLN, okay? And so from that point of view, a very natural equivalence relation is that of conjugation, right? It's a usual equivalence relation you put on representations. If you want to think more geometrically, you can identify the set of homomorphisms via holonomy with the space of bundles, flat bundles, say over some space whose fundamental group is gamma. This is maybe one of the reasons I think of gamma as a topological piece of data. Okay? And then the conjugation equivalence relation corresponds to changing the base point. So the Hom space itself is the space of pointed flat bundles, G bundles, over the space for which gamma is the fundamental group. And changing the base point is equivalent to conjugation, and so we get a natural equivalence on bundles. Okay? Okay, but this equivalence relation might not be very well behaved. It might the space of conjugation orbits might not be T1, right? As a topological space, it might be very complicated topologically. So a very natural thing to do is to try to fix this quotient space by removing some points that get kind of collapsed together by the equivalence relation. Okay? And so one possible way to do that, especially when G is not necessarily complex reductive, is to do the following thing. So since we've put a topology, a natural topology on Hom, we can look at the subset of Hom that has closed conjugation orbits. Okay, so the orbit is a subspace itself of Hom, right? A subset, and so it has a subspace, and you can ask whether it's closed with respect to the topology, right? And so we'll call these the polystable points. And decorate it with a star. Okay, and then that space is at least T1. Okay, just a priori here. Okay, and so we look at the set of the quotient space of under the conjugation action of this subspace, and we'll call that the G character variety of gamma. Now, given the restriction on G that we've made, namely that it's a real reductive group, it's more than just T1. Okay? In fact, work of Richardson and Slodwy from 1990 implies that this space is actually Hausdorff, and it's closed in a sense, or maybe complete is maybe a better way to say it, in the following sense, that there's a natural embedding of this space into some affine space, and with respect to that embedding, it has all of its limit points. Okay? And in fact, if you, of course, know that, then that implies it's Hausdorff, right? Okay. All right. Okay, so some special cases. If G is real algebraic, which it doesn't have to be, the general real reductive condition doesn't it doesn't imply it's real algebraic. It could be semi-algebraic, but not algebraic. Think like an identity component in GL and R, for instance. There's an inequality there to get the, right? Okay. Okay, so, but if G was real algebraic, then this resulting thing here, this quotient, is semi-algebraic, because that's very nice. Semi-algebraic spaces have a lot of structure that you can work with. They're triangulable and other things. Okay, so they're like a CW complex. You can play a lot of games with that to understand them. If G is compact, then all the orbits are closed, so we don't actually throw anything out. So this thing is just the usual orbit space in that case. Okay. And then if G is complex reductive, then actually this thing in the analytic topology on an affine variety, not the Zariski topology, this thing is actually identified with the geometric invariant theory quotient. Okay? Again, in the strong topology on the affine variety, okay, not the Zariski topology. And in that case, we can actually say something even kind of cooler, that this space actually is homotopic to the non-Hausdorff usual quotient. Okay, you have to think a little bit about what it means to define a homotopy with non-Hausdorff spaces, but in any event, you can, and they're actually topologically equivalent in that case. Okay, so, all right, I have a small audience that can ask questions here, and I have I don't know how big audience on YouTube Live, but the YouTube Live people can't ask questions, so are there any questions from my existing live audience behind the camera? No? Okay, all right. All right, so let's look at an example. It's just the simplest example we can imagine. Well, the simplest example is the trivial group. The modular fish is a point, not very interesting. Okay, all right, so the next simplest example is just no relations in one generator for gamma. Okay, so think like the fundamental group of a circle or something. Okay. And although the simplest Lie group case is C star, maybe that's a little too simple, because then the conjugation action is trivial, because the Lie group's abelian, right? And then in that case, the evaluation map just identifies the Hom space with the group, and then we just have C star back, for the gamma being just integers in that case, right? So that's a little too simple to give us any intuition. So the next example, simplest Lie group to consider would be like SL2C, okay? So rank 1 simple Lie group, okay, that's not abelian. And that's just here's the algebraic structure. We're probably all familiar with this. 4 complex variables subject to this one polynomial condition. Okay, all right. And then, okay, so then again, I already think I said this, the evaluation map is one generator here, no relations, and so the set of homomorphisms is just identified with just the group itself. Okay, not very interesting. Okay, so let's see what the moduli space is, okay? All right. All right, so for any t, I'm just going to define this matrix called epsilon sub t, okay? So it's just, essentially rational canonical form of a 2 by 2 matrix. All right. All right, so now any homomorphism such that t is not equal to plus or minus 2, so the trace is not plus or minus 2. Okay, that's because the trace of this matrix is just, right, is t. Okay, so the reason I'm excluding this is because the identity and plus or minus the identity has trace plus or minus 2. Okay, and there's 2 conjugacy classes there, so I'm going to exclude this at first. All right, so as long as this is not the case, if you write down the characteristic polynomial and solve for t or lambda or whatever variable you want to use for the characteristic polynomial, okay, you get 2 distinct eigenvalues, and it's determined by the trace. And so, consequently, well, maybe I won't bother with doing it. Okay, but consequently, there is a matrix that conjugates rho to this one. Okay, because their traces agree, and right, okay, and there's no, yeah, the Jordan canonical form or something is determined here by the trace as long as the trace is not plus or minus 2. All right, and because there's only one orbit, right, it has to be closed, right? Because if there was another orbit, they would have the same traces, and well, we've already ruled that out, okay, for this case. Okay, so we don't throw these guys out when t is not plus or minus 2. We keep all those values. Now, if t is plus or minus 2, you have 2 choices. Either you have epsilon plus or minus 2, okay? That's the one that's conjugate to something that's projectively unipotent, maybe. I mean, it's plus or minus 1s on the diagonal and a 1 in the upper right, okay? All right, or it's the identity, plus or minus, this is math boldface 1 there, okay? So plus or minus, that's not the number 1, it's a 2 by 2 matrix. Okay, the identity, plus or minus the identity. All right. So in the former case, right, you have this guy is conjugate to this. I just said that. Okay? And so now let's conjugate this by this matrix here. Okay? If I conjugate this by this, I get something like this. So conjugating by this stays in that orbit, right? But now letting n go to infinity shows, right, that within that orbit, right, I have a point that's not in the orbit of this matrix, right? Okay. And in particular, that limiting point is the plus or minus the identity, right? Okay. So that means that these guys did not have closed orbits. So those are the ones we throw away. Okay, they're not in the polystable locus. Okay, all right. And so there's that. And consequently, we have that the moduli space is just identified with the complex numbers. Every complex number gives you a value t. Okay, and the space is parameterized, the set conjugacy classes is parameterized by these matrices, except in the case where t is plus or minus the trace is plus or minus 2, in which case the plus and minus 2 values of the twice punctured complex plane get filled with plus or minus the identity matrix. And the other choices we threw away, right? Okay. All right, so that's a simple example. But you get to see so what choosing the polystable representations does for you. Okay, and how it fixes the topology. Because if I didn't do it, I'd have C with 2 double points. Okay, it wouldn't even be T1 because I couldn't separate those guys. Okay, all right. So in a similar way, if I instead looked at SU2 instead of SL2C, right, I still get the same. The trace still parameterizes the set of conjugacy classes. I don't have to throw anything away now because the Lie group's compact. Okay, but now the trace. What is the trace? Well, if we're dealing with unitary matrices, right? Every orbit has a representative of this form, and the trace is just 2 times the cosine. Okay. And so, what are the values of theta change vary? Right? It's between minus 2 and 2. Okay, and every one of those numbers corresponds to a unique conjugate class, and that's all of them. Okay, so that's what this modular space is. It's an interval. Okay, all right. And we can see already this is kind of interesting in a stupid kind of way, right? This interval, right, lives inside the previous example of C, right? And they're both contractible to a point, so they have the same topology. Okay. On the other hand, SL2C contracts to SU2. Okay, this is called the polar decomposition. Okay, all right. So let's just keep that observation in mind. Okay, this also shows that the character varieties are not always varieties, because this is not a variety. It's a semi-algebraic set, which is what I had said before, that when you, right, as long as your Lie group is real algebraic, the moduli space is semi-algebraic, and compact Lie groups are real algebraic. Okay. All right, now SL2R is less trivial than those two previous examples, but you still have the same kind of game you play. Okay, so you basically look at the what happens to the diagonalizable matrices. Okay, but now you have to be a little more careful. Right? Is it diagonalizable over R or C? Okay, all right. So if it's diagonalizable over R, you have these guys here, and now we're in the real field, so we can actually put an order on lambda. Okay, and so we can, since these guys are conjugate, right, just by the Weil group changing the order here, and we have in the real, and we can order elements in the real numbers, right? We can identify the set of matrices, which is equivalent to representations of the integers into SL2R, okay, with sort of two wings, okay, like two rays. So the complement of the interval from -1 to 1. Okay, so you have the ray going from 1 to infinity, and the ray going from -1 to -infinity. Okay? All right. Okay, good. I mean, you might say, well, what happens to the numbers in here? Well, you had those already, right? But the point is we made a choice, right, with the ordering here, right? So these numbers here, say, are bigger than 1, well, then these will be smaller than 1, right? But the ones that are smaller than 1 up here are equivalent to the ones that were bigger than 1 by switching the order, right? So, right? So taking that into consideration, the set of diagonalizable matrices over R is just this union of two rays up to conjugation. And then similarly, you have the set that's diagonalizable over C, but not R, right? And in which case you still diagonalize, you can still diagonalize the matrices, right? You have Z and Z, 1 over Z there. But now you have this additional condition that since you started off with a representation that was defined over SLR, not C, the trace has to be real. So you have a condition that the trace is real. Okay? All right. So if you write down what this is, and if you write down like Z as A plus IB or something like this, and you write down what this condition means, it's equivalent to saying that the norm of that complex number is 1. Okay, so these matrices are actually in SO2C. But we started off in SL2R, so you're in the intersection of these two groups, so you're in SO2R. Okay, and consequently you're in this. Your matrix has this form. Okay, now you notice something here, right? You have a minus sign on the anti-diagonal, and then you have another. You could put a minus sign here instead too. Okay. Now, those two matrices over SL2R are not equivalent. It's very subtle business. Over GL2R, they're actually equivalent. And over SL2C, they're equivalent, but not over SL2R. Okay, and the trace doesn't see this difference, okay, this sort of involution, switching the minus sign on the anti-diagonal. Okay? And consequently, these two matrices, the one with -1 here and 1 there, and with the same thetas, right? They are not equivalent under SL2R conjugation. Okay? And so this set of matrices actually is in SL2R is just defines an entire circle. Okay? And I just said that here. Okay. And I also mentioned that the traces don't distinguish those matrices. The Pfaffian does, by the way. The Pfaffian does. So if you put it all together, this is what the moduli space looks like. Okay, you have those two wings we had before, and then you have the elements that are essentially in SO2R. okay, defining a whole circle. That's what the moduli space looks like. But it also shows that this moduli space is the previous example, right, of SU2 showed that the moduli space is not always a variety, but this shows that the points are actually not always determined by traces or traditional characters. Okay, you have to use the Pfaffian to distinguish, points there. Okay, and so, right, because this point, say, and this point, right, are different points in the moduli space, but the trace would see them as being the same point. Okay, all right. So we already see here lots of stuff. In particular, this is another example that's not contractible, where the maximal compact subgroup of this SO2R, right, the moduli space here, deformation retracts to the moduli space of the corresponding maximal compact of the group. And we saw that with the previous example too. So that's going to be a general feature coming up. There's two examples of that. But we've also seen that character varieties are not always varieties, and they're not always determined by characters. So it's a little bit of a misnomer, except in certain cases, like SL2C, where it is a variety and determined by characters. Yes?
Sorry, what orientation stands for?
What's that?
Orientations.
There's no one.
You have these arrows. You have
Oh, there's no orientation. No.
Semi-infinite line.
Ah, it just means it keeps going. That's not an orientation. No. Yeah. I apologize for that. No, there's no orientation. No. This just means that the line keeps going. Yeah. I mean, I'm embedding it in R2, and so you should think of this as the honest circle centered at the origin, and this is like the ray emanating from the number 1 to infinity on the real axis, and this is the ray emanating from -1 to -infinity on the real axis. Okay, and the coordinates I picked to describe it, that's what it would be. Okay, good. And then, I already said this, right? This example, deformation retracts to this example. They're both contractible to a point, so maybe that would be a little bit ambitious to make a conclusion from that, but this one is more suggestive, right? This guy, deformation retracts to this one. Okay, neither is contractible. Okay, all right. Yeah, and SU, and I've already made this point that SU2 is maximal compact here, while this is maximal compact here. Okay, all right. So now we get to any further questions before I get to the next part, which is the definition? Nope. All right. So for any complex reductive group G, in fact, this is true for real reductive too. But anyway, if you choose the maximal compact, there is a natural inclusion of CW complexes. These are generally going to be CW complexes of this moduli space into here. Okay, it's not completely obvious, right? We threw points out here. We didn't throw points out here. Okay, so there's something to say with this, and the equivalence relation here is by K, right? The equivalence relation here is by G, right? They're different equivalence relations, so there is something to say there. But you can show that essentially it's the Weil unitary trick that since K is maximal compact in G, the orbit structure here is actually determined by K, and so you get a one-to-one map. Okay, all right. Okay, so with this inclusion in mind, we're going to say that gamma is flawed, okay, if this map is a strong deformation retraction for all G. Okay, and we're just going to quantify over the complex reductive G's, even though we could make this definition for other classes of groups within the class of real reductive. G, we're just going to define it for complex reductive. Okay? I like to think of this as a proper. So going back to what I had said before about the definition of character varieties, where we think of gamma as data that's topological, okay, and we think of G as data that's geometric. Okay, a Lie group sort of defines geometry. Okay. All right, you can think of that from lots of different points of view. From the bundle, the point of view, the viewing these spaces through the lens of modular space of flat bundles, you can think of it's natural there. You could also think of it through like Klein-Zerlangen program if you want. Okay, Lie groups correspond to symmetry groups. Anyway, okay, so I like to think of this as a property. So you need these two ingredients, topological and geometric, to define these moduli spaces. I'm quantifying over the geometry, so what's left is a property about the gamma. Okay? This is how I like to think of this, okay? All right. Okay, so we'll say that gamma is flawless, on the other hand, if this is not a strong deformation retraction for all non-abelian G. Now, these are not negations of each other, okay? You could have a gamma fail to be flawed because it failed for one, right, non-abelian Lie group, right? But that would not imply it's flawless, okay? All right. All right, and I'll say something a little bit more about where the name comes from. There's sort of two different points of view on this name. One, makes sense with respect to the word flaw being something wrong with the group, and the other is just purely egotistical. Okay, right. So here's the main philosophy, and I guess I've already said something about this, that quantifying over the geometric structure defining character varieties, namely the Lie group, gives group theoretic properties about gamma, and such persistent structures should be understood as a general feature in group theory, perhaps geometric group theory, depending on your point of view, geometric group theory. Okay. Any questions so far, or more questions? I've already had at least one, but I think one. Okay, all right. All right, so the first result is actually a couple of results from 2009 and 2015. This is actually, when I first met Carlos, I was, pretty close to fresh PhD, and I was doing my second postdoc in Lisboa, and Carlos was my postdoc mentor. I think I was your first postdoc student, is that right?
I think so.
Yeah, yeah. And anyway, so our first paper together it resulted in the 2009 publication. Although we had come up with most of the ideas for the proof a few years earlier, it just takes a while to get things published, right? All right. But the theorem was just for complex reductive groups, and we showed that with the definition I just gave, that finitely generated free groups are flawed. Okay. Now a few years later, we started thinking about the real reductive case, and Andre and Anna and Carlos and I generalized Carlos is my previous work to the real reductive case. Okay, and that was published again a few years later after we come up with all the ideas for it. Anyway, and that's what we'll say is real flawed. Okay, so if the same definition for flawed holds, but now quantified over the bigger class of Lie groups of real reductive Lie groups. Okay, okay. And the examples I gave before illustrated two simple versions of that, right? With SU2 versus SL2C, and then SO2 versus SL2R. Okay, all right. And then, of course, one naturally wonders if the situation generalizes to any arbitrary finitely generated group gamma. I mean, because, right, the Lie groups deformation retracts, so why not the moduli spaces, right? Okay. And you can find counterexamples from Atiyah, Bott, and Hitchens' work much earlier, and we already noted these in our original paper, right? That this was non-trivial. Okay. And in our original paper, we also asked the general question, and in our original paper, we also looked at some other groups other than free groups, at least in some cases. But anyway, okay. So here's a sketch of the proof, at least in the complex reductive case. Okay. Although the real reductive case is actually not that different, given that work of Richardson, which generalized a lot of the facts that are used in the proof for the complex reductive case. Okay, so basically the main ingredients are Kemp-Ness theory and the general Lie group polar decomposition, and Whitehead's theorem. So basically we have the character variety for the free group, okay, and then you see that there's a quotient space by the compact group here, okay, not the Lie group G, okay, and so there's a natural projection because you're increasing the equivalence relation, okay, and then what Kemp-Ness theory does is defines this section. So for every orbit here, okay, and maybe it's natural to think of this as now the GIT quotient, okay, in this setting, although you don't have to, but for every from the GIT point of view, from every extended orbit equivalence class, you pick out a K orbit, okay? And this is essentially Kempf-Nest theory. You define a functional, okay, a translation function, okay, and then you embed everything inside a big affine space where you can define a K invariant Hermitian norm, and then you define a translation length function, and then you look at a minimum of that, okay? And this is a K invariant minimum, and so it picks out a K orbit, okay? So this gives us a map up here, okay? This is the natural inclusion we talked about before. This is just the identity map. I mean, it's the identity inclusion, okay? And the same thing here, because all three of these here are K quotients. This is, again, a projection here. So then what happens up here, right? Well, you see, we're quotienting by K in both situations, right? So forget about the quotient by K just for a second, right? On the level of Hom, since we're dealing with free groups, the Hom space is just an R-fold product of G's. And this is an R-fold product of G's here as well. Now, this is where the second ingredient comes into play, okay? The second ingredient is a general fact that for any complex reductive group, there's a K equivariant deformation retraction from G to K. Okay? In fact, this is actually true for any Lie group, really. I mean, okay, this is a very, very general statement. Okay, but the polar decomposition makes this very nice because the Lie group itself topologically decomposes into K cross an affine space, and you just contract the affine space away. Okay? All right. And the deformation retraction on the level of Lie groups is K equivariant. So it descends to a deformation retraction of quotient spaces. Okay? You first have the one for G, but then the Com space is a product of G's, right? And so you get deformation retraction, or a product of deformation retractions is the deformation retraction. Okay? All right. So you now have a deformation retraction from this to here. This is stable on the inclusion there. Okay? And then and so to get the deformation retraction from here to here, you just follow through with the Kempf-Nest theory. Okay? And basically that's it. Okay, and you might say, well, where's Whitehead's theorem come into play? Well, that's a way to cheat the system, okay, like without cheat the diagram. Okay, so the Kempf-Nest theory actually gives you a deformation retraction from here to here. Okay, on the other hand, oh no, sorry, I take that back. Deformation retraction from here to here. Sorry, that's what I meant to say. Okay, that's the Kempf-Nest theory, and then no, sorry, that's part of it. And then there's also a deformation retraction from here to here from Kempf-Nest, okay? So now you have that these two are homotopic and these two are homotopic, okay? And it's not generally true that strong deformation retractions are transitive, okay? But if this inclusion is an inclusion of complexes, then Whitehead's theorem implies that actually there is a deformation retraction. Okay, so these two being homotopic and these two being homotopic implies these two are not just homotopic, but strong deformation retractions. Okay, I mean, homotopy equivalent is transitive. Okay, so these two being homotopic and these two being homotopic imply these two are homotopic. Okay, that's just for free. But to get that these two are strong deformation retractions of each other from the SDR here and the SDR here, now we have to use the fact that this is an inclusion of cellular complexes and impose Whitehead's theorem. Okay, all right, anyway. So there's sort of two different proofs in this slide of the same fact. Okay, all right. Using just these two facts requires a little bit of diagram chasing here to make sure this thing actually is commutative and everything's continuous, in particular this thing, in the right way. Okay, using Whitehead's theorem allows you to cheat that a little bit. Okay, but then you got to think about CW complexes on semi-algebraic spaces and stuff. And anyway, bottom line, you can make it all work. So, all right. So the next case of flawed groups, and real flawed, is finally generative abelian groups. Okay, and again, in the 2009 paper, we already gave a proof of this for some G. Not all G, but some G. Okay, like GLN, SLN. I think the proof we gave also works for SP, the symplectic group. But it doesn't work for all Lie groups. Okay, and this was pointed out to us, and so we said, okay, well, let's prove it because I'm sure it's true. So we went ahead and did so. And it turned out there was other people working on similar ideas, more focused on the Hom space, not the moduli spaces. Okay, and so there was discussions between different groups of researchers and stuff. Anyway, bottom line is we ended up coming up with a very nice proof. Some parts of it inspired by work of Soto and his collaborators. to prove that finely generated abelian groups, even those with torsion, okay, not just free abelian groups, are both flawed and real flawed. Okay? And basically, the proof is actually different than the other one. The polar decomposition doesn't work. Okay? So this stage up here, doesn't work for commuting matrices. In fact, Soto has shown that there is no factor-wise deformation retraction from products of G that commute to products of K that commute. Okay, it doesn't, even in the SLN cases, I think there's counterexamples. Okay, so this method isn't going to work in that case. All right, so we cheat the system. And so basically, we use, so this is a little bit of a misnomer. Okay, here A is an abelian group, a finely generated abelian group. GSS is a set of semi-simple elements of the Lie group. Now, this is equivalent to elements in the Lie group that have closed conjugation orbits. Now, that's not a subgroup. So HOM A to GSS doesn't really make a lot of sense at a first glance, okay? Because there are no homomorphisms unless this was a subgroup. Now, but I claim that the notation actually does make sense because you see, we've already shown that whenever A is finally generated, right, the set of homomorphisms can be identified with a subset of products of Lie groups. And so you can ask which of those, tuples have semi-simple elements in the tuple. That's what this set is. Okay? And it is conjugation stable. Okay? So you can look at it, and then you get a subspace of HOM. Okay? And you can, and it's conjugation stable, so you can look at its quotient space. Okay? Now, one can show that this is actually exactly the set of polystable representations, the ones that have semi-simple elements. So the things you would have thrown out to make the moduli space is exactly the things that didn't have semi-simple entries. Okay? So that's there's something to do. Okay? But that's one of the steps in the proof. Okay? It's not obvious. Okay? But it is something to do. All right. On the other hand, you can define what's called the elliptic elements in G. Okay? And the elliptic elements in G are the things that are G conjugates of the maximal compact. And likewise, we can define a set of homomorphisms as with elliptic. This is not a subgroup here either, but we can look at the set of tuples, right, that come from the evaluation map of this abelian group, so that the outputs are elliptic. Just like we did the same thing here, where we're requiring the elements in the tuple to be semi-simple. Okay? And this is also a G-stable space. I mean, it's by definition. I mean, you can just see it immediately, right? They're all G, the elements in the tuple are all G conjugates, right, of K. So you conjugate a G conjugate of K, it's still a G conjugate of K. Okay? And likewise, semi-simplicity is preserved under conjugation. So it's also prima facie clear that this is also, right, stable under the conjugation action, right? Because you take a G conjugate of something with a closed orbit, well, it has a closed orbit. Okay. The entries. Right? Okay. All right. The statement that these are exactly the polystable ones is not obvious. That's a little theorem. Okay. Right. So these are like the this is the semi-simple representations. These are the elliptic representations. Okay. Sorry. And then there's this isomorphism. With in both cases, the isomorphism is not obvious. So just like up here, if you have a tuple of elements that have closed orbits and the whole orbit is closed of the whole representation, and vice versa, that's essentially what this isomorphism is here. In the same way here, or not the same way, but in a similar way, if you have a tuple of elliptic elements, so every entry is a potentially different G conjugate of an element in K, because they commute. This is essentially the feature here, right? This is not true for a non-abelian group. If A wasn't abelian, this statement would not be true. If A is not abelian, this statement would not be true. Okay, but because they commute, the sort of the closed orbits individually being equivalent to closed orbits globally is true. And in exactly the same philosophical idea, being a G translate of K, being an elliptic element, locally or tuple wise, is equivalent to globally being a G conjugate. But of course, if it's globally a G conjugate, right, then you might as well just have quotient by K to begin with, right? Yeah, and so that's what's happening here. So you have a potential different G translate of a bunch of K things, but because they commute, you can uniformize that to a single G conjugate of all the, of a unitary representation. Okay. All right, so that's the first two steps. Okay. Now you use the fact that the now we're not in the moduli spaces, we're on the Hom spaces. Okay. Now here we construct a G equivariant deformation retract from the semi-simple elements to the elliptic elements, the elliptic representations. Okay? This is called the eigenvalue scaling thing. So every entry here is since it's semi-simple, is essentially diagonalizable. In the SLN case, this is literally the case. Okay? In the general G case, you have to do an embedding and put it in the maximal torus instead. But the bottom line is, if they're semi-simple, you can with respect to some embedding, linear embedding, okay, of G into some GLN, you can define an eigenvalue scaling. You can consider yourself being, right, not in a single maximal torus, that's not a true statement, but you can, with respect to some ambient group, you can put them all in a diagonal matrix. Okay, and then you can scale the eigenvalues, okay? And if you scale the eigenvalues, right, then now you have some G translate of something unitary, right? I mean, just almost by definition, okay? All right, and the main idea is semi-simple. This is what I just said, semi-simple. I forgot that I put this here. I was just explaining it. Okay, anyway, semi-simple elements are diagonalizable, so we can contract them back to the eigenvalues. Okay. All right, so, oh, sorry, that's the end of the proof. So that's the point. If it's G, and this is G equivariant, so that means that this mod G is deformation retracts to this mod G. But we've already shown in the previous two steps that this mod G is that, and this mod G is that. So this deformation retracts to that. The end. Okay, that's the end of the proof. Okay? Now, this is a real subtle thing here. We did not show that there was a so in the free group case, right, you end up having a K equivariant deformation retraction from this Hom space to the Hom space corresponding to the unitary ones. Okay? That's a very strong condition. We did not show that here. We had to get rid of some things here and restrict our attention to a bigger set of representations, not the unitary ones that we're after, but the elliptic ones. And then because we happen to be dealing with abelian groups, representations of abelian groups, when we construct the moduli space, the discrepancies disappear. Okay? But it's much stronger to show that the total Hom space is K equivariantly deformation retract in the right way. That's what we had in the free group case. Okay? Now later on, and we're going to come to this in a couple slides, Bergeron actually shows in the abelian case, in fact even more generally in the nilpotent case, that this stronger condition is in fact true. Okay? And this stronger condition being true actually gets you a lot of mileage. Okay? Anyway, we'll come to that though again. I'm just kind of letting you know what's things to come. Okay, all right, so what about flawless groups? So Carlos Florentino and Indranil Biswas, after we had done, I guess this is in between the abelian case and the free group case. We had already pointed out that certain surface groups did not have this property. Okay, in the 2009 paper from Hitchin and others. Okay. And T and Bond. But you could ask the question, which the defining property of flawlessness are those counterexamples special, or is this always, these deformation retractors always fail? Okay, and that's what they show. They show closed surface groups of genus at least 2 are flawless. Okay, they in fact those deformation retractions for those finally generated groups never work if G is not abelian. Okay, if G is abelian, then you get some things trivially work. Okay, in this case at least, because in that case the defining relation for the closed surface group it just trivializes. Okay, and you end up with just a product of the G's. Okay, and then that works. Okay, so here's just a sketch of the proof, very, very sketchy, very, very sketchy. Okay, so here, gamma G is your fundamental group of your Riemann surface of genus at least 2, and then so now you use non-abelian Hodge theory. So this thing is homeomorphic in this case to the space of G Higgs bundles, okay, and then the unitary representations are homeomorphic to the moduli space of flat principal G bundles over that. Okay, so Neresima Shashadri. Okay, all right, or vector bundles, I guess is like the way to think about it. I mean, for general G, I guess you want what I wrote, flat principal holomorphic G bundles. Okay, in the unitary case, it's holomorphic vector bundles. Okay. But here, you can think of these two as being related in the sense that this guy here is the zero Higgs field versions of things here. Okay, so this moduli space sits inside this one. Okay, all right. So so from the viewing of these spaces through the lens of Higgs bundles or holomorphic G bundles, you can compute Betty numbers of the moduli spaces using that theory. Okay, and then you can just compute sufficiently many of them, probably doing something like this retraction to the nilpotent cone and things like this. Okay, I'm not going to go into, nor am I really qualified to talk about in detail. But anyway, you do these computations, these cohomological computations, and you just identify Betty numbers in each case that are not that are different. And so consequently, they can't be homotopic. The moduli spaces can't be homotopic because if they were, the Betty numbers would correspond, right? And so that's all there is to it. You don't have to compute all the Betty numbers in every case. You just have to identify one special case, okay, in each that one corresponding special case, okay, and show that they're different. And that's essentially what they do. Okay. Did you want to say something more? Or?
Yeah. Which is the middle dimension?
Which I was about to say it's the middle one, but I didn't know. Okay, yeah, it's the middle one. Yeah. I was about to say that, but
because in the compact case it has to be one by Poincare duality, let's say.
Yeah.
And it's not one
in
the Higgs bundle.
Yeah, that's what I remember from reading the paper too. But it's been a few years since I've actually looked at it in detail. Okay. So here's a good point for this remark if you generalize this point, this example, away from surface groups, hyperbolic surface groups, then you're thinking of fundamental groups of Kähler manifolds. Okay? And in that setting, you still have a non-abelian Hodge theorem, right? The character variety is now homeomorphic to the moduli space of G Higgs bundles over this Kähler manifold with not just flat, right? We want all vanishing Chern classes. Okay? All right, not just one, not just sorry, I mean, what do you mean by flat? I mean, not just the curvature is zero, but you need all the Chern classes, right? Okay. And there's plenty of more general versions of the non-abelian Hodge theorem. I'm not going to state them all. This is the only one I need for this particular point remark. And likewise, in that case, you have a moduli space of flat holomorphic principal bundles over G, and we'll let the Higgs bundles be M, and the holomorphic principals be N. And in this setting, in this generality, this guy is naturally a subspace of this guy, again, by Higgs field 0, okay, just like in the previous situation. But now we can make another observation, that if we look at the cotangent bundle of N, right, that's essentially adding a Higgs field. The Higgs field really is like a direction vector, okay? But this space here is not equal to this, right? There's actually like limit points. There's boundary divisors, okay? And so this space is actually a partial compactification of this space here, okay? Now, this space, cotangent bundles always deformation retract to their base space, right? So these two are homotopic, right? But the fact that this is not equal to this, that there's in fact boundary divisors that you need to add, right? Think like the North Pole in a punctured sphere, right? Right? You would think that adding boundary divisors should change the topology, right? So the existence of a deformation retraction, right, is somehow weird, right? Somehow it's saying that those boundary divisors you're adding really aren't changing the topology at all. And it's through that lens that this just says what I just said. Boundary divisors you expect to change with the homotopic type. It's through that lens that we might say gamma has a deficit or is flawed. Okay? Now, the egotistical way to think about it is FLA is right, Florentino, or FL, sorry, is Florentino, and LAW is Lawton. And we define this property, right? Okay, so this is maybe, maybe this is too egotistical, except for the fact that it's a negative word, so maybe it's acceptable if it's slightly self-deprecating. Anyway, okay, but I think this lens might be the better one to think of it that way, so then we can claim we're not being too egotistical. Okay. All right, so what time is it? Okay, good. All right. So the next case is generalizing abelian groups. We get finally generated nilpotent groups. Those are the ones that have the lower central series terminate. But I already mentioned Bergeron's work. He showed that finally generated nilpotent groups are flawed and real flawed. And the really cool thing he did here is he did two cool things. I mean, one, he used both the ideas from our previous two papers, the Kemp-Ness theory and eigenvalue scaling. In our two previous papers, we used one and not the other. He put those methods together, right? And in doing so, he was able to show this stronger property than we were able to show in our abelian paper, right? He was able to show that there is a k-equivariant deformation retraction. It's just not the one that we knew didn't exist. It's not the one that is factor-wise scaling. I mean, factor-wise deforming. Okay, it's more complicated than that. But there is one from the total Hom spaces. That's k-equivariant. And the other cool thing is that the key new idea, these two methods were already sort of out there and used to address exactly these two questions, is that he showed the Kemp-Ness set consists of normal representation. So these are things that like commute with like conjugate transpose, okay, or more generally the Cartan involution, okay. And one of the key ideas here is that if you use Kemp-Ness theory to get down to the Kemp-Ness set, then you calculate and show, which is what is the really cool idea was that this set is the set of normal representations. Generally, you can say that they always live in the Kemp-Ness set, but they're not generally equal. But for nilpotent groups, they're equal. Okay. So then you do the eigenvalue scaling, and now you get something elliptic, just like I had mentioned before. But here's the cool thing: elliptic in normal is unitary. And so you're there, okay? Okay, so this is a really nice paper, and we use that. We generalize his work and unify all known cases, and put together all the existing methods and techniques to prove that, which honestly you can pretty much glean this from his work, knowing our prior work. It's almost like a corollary of those two theorems. But I think it's really important and nice to put together, unify cases and put together ideas. So I'm highlighting it, or we're highlighting it, I think, with that in mind. So free products of nilpotent groups, finally generated nilpotent groups, are flawed and real flawed. That's the new theorem, one of the new theorems we have in this paper. And so the property that you have a k-equivariant deformation retraction from the Hom spaces, we're going to say that's strongly flawed. Okay? And in general, we proved strongly flawed implies flawed. Okay? And we also prove, in general, it doesn't matter what gamma is, free products of finally mainly strongly flawed groups are flawed. Okay? So now we put that together with Bergeron's theorem. He doesn't really state it in his paper that nilpotent groups are strongly flawed. He uses it as a technique. But if you read his proof, he actually is proving that they're actually strongly flawed. And then you put that together with our previous, these two general statements that are independent of gamma, right? I mean, for any gamma, strongly flawed implies flawed. And for any gamma, free products of strongly flawed are flawed. Okay? And you go into the nuts and bolts of Bergeron's proof, and you see that free products of nilpotent groups are flawed. And this includes both the free group case, the abelian case, and Bergeron's result, and other cases that are were not known before. Okay, so it extends the class of flawed groups and unifies all known cases. Okay, but the proof honestly is not that hard. Okay, especially if you've been thinking about these things.
Sorry.
Yeah, go ahead.
The strongness is in general lost with free products. And if you have strongly flawed groups,
yes.
and you take free products of them.
Yes. Oh, yeah, no, it's strongly flawed. No, it's yeah. I just was emphasizing it here just to make this. Yeah. This statement's actually a little stronger. Free products of strongly flawed groups are strongly flawed. Yeah. No, there's nothing else. Yeah, they're strong. I just was, yeah. I was, yeah. I should have said strongly flawed. Yeah, that's right. Yep, good observation. Okay. And I got just enough time, I think, to just end here with the last class of groups we'll consider. So right-angled Artin groups. They're essentially groups that arise as, you have a bunch of, the only relations that you can have are commutator relations. Okay, so free groups are examples of right-angled Artin groups. Free abelian groups are examples. Those are two extreme cases where you have no relations, and the other case, we have all maximal relations. You can organize these things via a graph. The generators are the vertices of the graph, and then you draw an edge if there's a commutation relation. Okay? All right, so free groups have no edges. Free abelian groups have maximal number of edges, the complete graph. Okay, and and then everything else is in between. So one of our other theorems says that if you have a right-angled Artin group that's star-shaped, the graph is like an asterisk. So there's one vertex. Oh, well, I shouldn't say one vertex, but it's, it has the shape, right? Right. Okay. So it's the simplest example, really, of you say a tree, a contractible graph. Okay. And indeed, we believe that this can be generalized to that, pretty much using induction with the existing proof, although that's a work in progress. And that's a conversation that is Bergeron and Carlos and actually Clement, Guerin and I are all talking about this, generalizing some of these ideas. Okay, so these rags are flawed, and moreover, if you have any connected rag, even if it's not contractible, there's a component of the character variety that satisfies the flawed condition. Okay, we weren't able to get the whole character variety, but we have a natural component. Okay, that has that property, and we'll call that property special flawed. And basically the proof comes down to utilizing the idea of normal intersect elliptic is unitary. So we take that idea from Bergeron's paper and apply it to general rags as far as we can. Okay, and then the very last result, which is we wanted to ask whether virtually flawed groups were flawed. Okay, and we weren't able to get that statement or anywhere near it, but we had some special cases that if you look like finite by free, it's flawed, and then finite by nilpotent is special flawed. There's a component in that case that works. And the methods are essentially the same methods we used with the previous one. And I should say that there is a new technique here for star-shaped rags. This new technique is using a different kind of decomposition, using the KAK decomposition of the Lie group instead of the polar decomposition. But aside from that, that decomposition is similar. We use similar ideas with that decomposition. I mean, it's not exactly the same, but anyway, I'm already over time, so maybe I'll just pretty much end here. We have some conjectures. We've shown that connected rags are special flawed. So our star-shaped rags and star-shaped rags are flawed. So a big conjecture is all rags are flawed. I guess this is already in our. This was in our abelian paper, but not in our original paper. Yeah. Okay, and then work from Vicente Munoz. He wasn't thinking about flawedness at all, but he was just computing the geometry of torus knot groups, okay, and looking at his computations for SL2C and SU2, you can see that there is a deformation retraction just from looking at the geometry. And so one can generalize the class of torus knot groups to a class that looks like this. We call it generalized torus knot groups, and we conjecture that based off the existing computations that these are actually flawed groups. We know that closed hyperbolic surface groups are flawless. We conjecture that all non-abelian Kähler groups are flawless. We have to put in non-abelian because the abelian case is flawed by lots of observations. You can see that both from the Higgs bundle point of view. I think Carlos and Jernil actually wrote a paper directly using that point of view, but it also follows from our paper. that came earlier. Okay, and then you can look at, if you want to generalize nilpotent groups, you could ask about these so-called supersolvable groups. So are finally generated supersolvable groups flawed? Another question is, you have free products of nilpotent groups are flawed. What about graph products of nilpotent groups, right? You can go a little bit more general with it than free products. And lastly, thinking like a geometric group theorist, you can ask the question that I think is pretty hard, but very interesting. If two groups are commensurable and one is flawed, is the other one also flawed? If that theorem was true, we definitely would find ourselves in the world of geometric group theory unambiguously. But I've tried to think about this a bit, and I haven't got any real good ideas. So if anybody out there in TV land has any ideas, feel free to let me know. I'd love to talk about it. Okay, and so that's it. So I know I went over a little bit. I apologize for that. This is today's theorems were brought to you with the help of the Simons Foundation. And all this work that I discussed is in collaboration with Carlos. And here's some, you can find my arXiv postings. The free group case was in Anolin. The free group in our real flawed was in Forum. Topology and applications had our work on abelian groups. And the one that had the theorems today listed as 2021 is in our new paper on the arXiv. And this is where we kind of unify things and extend things and give them some names. We also do some general technical stuff which kind of deconstructs the concept, right? And says, okay, well, if you are quantifying overall reductive groups, what if you know it's true for just the simple ones or just the adjoint ones, right? Can you bootstrap your way up from certain special cases, classes of the Lie groups all the way to all the reductive or something? So we have a whole section where we're exploring that in detail. I didn't talk at all about that here, but I think that's worth noting. Okay, so now I will end finally, and thank you all for being here and out there if you're out there. And I'm always open to questions, but I don't know how you end a seminar when it's being live streamed. So I'll let you do that, and I'll just stand here.